Welcome to Pre-Calculus. Today we will investigate numerical function composition, focusing on whether or not function composition is commutative. We've looked at two examples where we composed functions, leaving the x value. Let's take a look at two examples where we evaluate numerically. For this example, I've got two functions, f of a equals a plus 2 and g of a equals 2a plus 4. My task is to find f of g at 0. I'm going to rewrite that function composition expression just to show what I'm composing into what. Remember, I can write this using the circle notation, or I can write it using nested functions. So this is equivalent to f of g. And here specifically, I'm composing in the number 0. Let's make the function composition first. So I'm going to pick up and just decide what's f of g of a. And then once I decide that, I can substitute in the 0. So I'm going to pick up the f function. That's the overarching function. It's on the outer side of the composition. So that's going to be a plus 2. So recall where I see the a value, I'm going to leave a gap. And then I'm going to write plus 2. And then in that gap, what I need to write is the g function. I'm substituting in g, its range for the old domain of f. So that's 2a plus 4. But then I need to also consider that I'm substituting for a here the number 0. And that gives me this expression. And notice at that point, that's all numeric. I don't have any variables in that expression. So let's simplify that. I'm going to treat the inside first. So 2 times 0 is going to give me 0 plus 4. 0 plus 4 is 4. And then if I add the 2 from the f function, I see that f at g at 0 has a value of 6. We'll circle that. I do want to check to see if the composition here is commutative. In other words, can I switch the order and compose f into g? Would I still get 6? Let's check it. We'll set it up for g of f of 0. So I'm going to record that with the nested notation, g of f. And then I'm going to substitute in 0 for a. And then let's record that function. So this direction has g as the overarching function. So I'm going to write 2 where a was, I'll leave a gap, plus 4. And then within that gap, I want to put the entire range of the f function. So that's a plus 2. And then as a final step, I need to substitute a with the number 0. Again, let's check and see if this comes out to 6. Is function composition commutative? Can I switch the order around and get the same result? Well, on the interior of the parentheses, I've got 0 plus 2, so that ends up being 2. So 2 times 2 is what's left. That's 4. And add 4 to that gives me a sum of 8. And when I check to see whether or not these are the same outputs, I see that, lo and behold, they are not. They are not equal, which supports what we saw with just plain function composition with variables, that the composition is not commutative. We'll make that claim here over on the left. Function composition is not commutative. Let's take a look at one more example. Scroll up here. That example we just worked on was a linear example, 2 linear functions. Here we've got a linear g of n, that's 3n plus 2, in addition to the cubic. In fact, it's a polynomial expression for h, n cubed plus 4n squared. So note the direction here is g of h at 3. So I'm going to start again by rewriting that with the nested version, g of h. And then instead of the n variable, I'm substituting in the numeric value 3. Let's calculate this direction. So I'm going to leave the g function as the overarching function. 3, where I see n, I'm going to leave a gap. I'm going to sub in the f function there where there was just n. I'm sorry, the h function. So that's going to be n cubed plus 4n squared. But then I've got to recall I'm not dealing with just variables. I actually have a number I'm substituting for n, and that's the number 3. So I'm going to substitute that in. And I'll go ahead and put parentheses around the number. Not totally critical because it's not negative. Good practice though. Let's simplify this expression now. Notice it's all down to number values, no variables. So within the parentheses, I'm going to start cubing. 3 cubed is 27. 3 squared is 9 times 4 is 36. So I'm going to add those two numbers together. 27 plus 36 is going to give us 63. And then I need to multiply that by 3. Right? Build my expression again. And let's multiply 63 times 3, and that's going to give us 189 plus 2 would give us the total simplified number of 191. Let's check again. We've already seen that usually function composition does not commute. Let's check with this one. Perhaps this one is different. So let's check the other direction. Let's put h as the overarching function and substitute g within h. We're going to compose that function, and then we will check for the value at 3. Here we're going to start with the h function. So it's n cubed, so I'm going to put my parentheses where the variable was to the power of 3 plus 4. There's another variable occurrence that is squared, so just like I did, I'll leave parentheses there for that. And within those two parentheses, I'm going to compose the g function. So this is 3n plus 2 in both locations. One more change, I need to sub out n for the actual value of 3. Place that in both locations again. For this direction, we want to find that 3 times 3 plus 2 is in both of those parentheses before we cube or square. So let's do that first. 3 times 3 is 9, plus 2 is 11. So within the parentheses, I've got 11, and then it's cubed on the first term, plus 4 times 11 squared on the second term. So 11 cubed, we need to do some arithmetic. I know 11 squared is 121. So I'm going to multiply 121 by 11. And that gives me 1,331. And to that 11 cubed, I'm going to add 4 times 11 squared. So that's 121. That's 11 squared times 4, which is going to give me 484. And then to complete the sum of 1,331 plus 484, we would get a 5 in the units place, a 1, an 8, and a 1. So 1,815. So we've done that function composition for this g of n and h of n in both directions. when we compare the outputs, looking to see if this function composition commutes, or I can switch the order, I see that 191 does not equal 1,815. So again, I'm forced to conclude function composition is not commutative. We'll write that here again. We've written it several times, so it's something we're seeing recurrently. We need to ask though, is it ever commutative? We don't see it as a general trend. When is function composition commutative? Well, let's take a look at one final example that goes back to variable equations. So here I've got two equations, f of x equals negative 2x cubed plus 2, and g of x equals the cube root of x minus 2 over negative 2. So let's see if these two equations compose and we can get the same output from both directions of the composition. So we'll start with f of g of x. And f will be the overarching function. G of x will compose within f of x. So I'm going to leave this structure. So note that the f function is a cubic function, negative 2. Where I see x, I'm just going to leave a gap. And then I'll finish the rest of the structure. So it's cubed plus 2. And then within the gap where x was, it's going to place this whole range value or function value of g. So that's the cube root of x minus 2 over negative 2. So we need to simplify this expression, and where I start is here in this parenthesis group. So I see that I've got a cube root cubed, and I'm going to notice that that cancels. The cube root cubed is their inverse operations, and so that just simply cancels. So my next step would be to record negative 2 times parentheses of the fraction x minus 2. Notice the radical is gone, the cube is gone, and it's just the rational expression there, x minus 2 over negative 2. On the outside, we are adding 2. What I'd like to cancel next are my coefficient in the denominator of that blue fraction. So negative 2 divided by negative 2 cancels. And notice how the function is simplifying down. Now I've got x minus 2 in parentheses plus 2. And at that point, I can let the parentheses go. There's no coefficient out front. And I see that the last two numeric values, negative 2 plus 2, also cancel. And this composition simply results in x. Well, let's check the other direction. Let's let g be the overarching function, and we'll compose the f function within g. G is a cube root function, so we've seen it subbed in before in our previous direction. So I'm going to write the radical large because at this time, when I write x, I'm going to leave a gap. Minus 2 over negative 2. And within the gap, I need to compose the entire range of f. That's going to be negative 2x cubed plus 2. And that composition's complete. I just need to simplify. So at that point, I can let the parentheses go within this numerator expression. Once I do that, I see I have an immediate cancellation of 2 minus 2. What I have left is the cube root of negative 2x cubed, all divided by negative 2. So at that point, I see a division cancellation. Negative 2 divided by negative 2 becomes 1. And this now equals the cube root of simply x cubed. And at that point, I also see that the cube cancels with the cube root. And this one, like our previous example, also yields the value of simply x. So in this case, with these two particular functions, we do see that the outputs are equal. And so we need to ask ourselves, what's going on with f of x and g of x that allows me to run the function composition so that the output is x in both directions? Well, what we can conclude from this demonstration is not that all function composition is commutative, but that composition of inverse functions is commutative. And in fact, it specifically reduces to x, which is our identity function. So let's record that here over on the left-hand side. And what we'll do is we'll approach this statement from the point of view of two functions being inverses. So what we'll write is two functions are inverses of each other if both directions of composition, like we've demonstrated for f of x and g of x here, result in x. And again, what we're saying with x is that they result in the identity function, f of x equals x. In fact, we could write it here, if we called our functions f of x and g of x, f of g of x equals x, and g of f of x equals x. And that really is the special case where we do see that function composition yields the same result one direction as the other if two functions are inverses of one another. Thank you for joining for this investigation of function composition. See you soon.